explain why the sum of three consecutive integers is always divisible by 3. So if I just write some down, 1 plus 2 plus 3, I get 6. So I see it works here. If I do 2 plus 3 plus 4, I get 9. What we can see is I'm adding, well, because I've got a multiple of 3 here, I'm then adding 1 to each of my terms. So I'm also going to have a multiple of 3. And as you carry on up, we're going to remain having a multiple of 3. Or if we went the other way and minus 1 from each of them, so it would be 0 plus 1 plus 2. We'd again get a multiple of 3. It must always be that way. I thought that's a pretty solid argument, to be honest. But this question, in the mark scheme at the very least, expects a bit more, and that is to use an algebraic proof. But I think if you write these down and then justify it like I just did, I think you're pretty much there. So algebraically, we could actually say our first integer was x, and then we've got x plus 1 as the next one, and x plus 2. This is a perfectly fine way of doing it. There is an even better way, though, so which I'm going to revert to, and it is instead to call the middle number x, and then x plus 1 and x minus 1. The nice thing about this is that the minus 1 and the 1 cancel. We've got the same, we've basically got just one more to the right of the middle number and one less. So we end up with 3x. I should probably just say, like, oh, well, I would write, let's x plus 1, sorry, let's x minus 1, x plus 1 be the three consecutive numbers for any some integer x, add them together to get 3x, and this is necessarily a multiple of 3. So a great little proof here. Note the idea of using x minus 1 and x plus 1. You could do it this way. You just end up with 3x plus 3, which you then factorize as 3 times x plus 1. It's just even neater if you do the one below. So yeah, this is a great argument for showing that the sum of any three consecutive integers is always divisible by 3. For part 2, it says, is it true that the sum of four consecutive integers is always divisible by 4? So there's two ways to go here. We could try and find a counterexample where it's not divisible by 4. And in fact, this is very quick, because if we do 1 plus 2 plus 3 plus 4, we get 10, which is actually equal to 2 times 4 plus 2. So counterexample, not always divisible by 4. It's actually a very powerful idea in proof of mathematics. There have been significant conjectures or ideas in maths that have withstood hundreds of years of people trying to prove them. And actually, the opposite has happened in the end. Somebody has managed to find a counterexample. So there's no point in looking for a proof. It would never actually exist. In this case, I'm going to go a little bit further and show you that we can prove it's never true. But I just want to really state it's not a trivial idea. This is a really big idea. And I'm going to just share with you an example. So this is a conjecture by one of the greatest mathematicians of all time, Leonhard Euler. And he said that it's impossible for two positive cubes to sum to a cube. In fact, this is shown to be true because um, it's a it's a one aspect or one particular case of Fermat's last theorem, which I'm not going to talk about, but I would advise you look it up. So what Euler did was sort of build on the idea of Fermat's last theorem, but add his own little twist to it. So he said it is impossible for three positive fourth powers to sum to a fourth power. So we can't ever write anything like this with integers. And then he just carried on going up. And he conjectured this in 1769. But in 1966, so we're talking just under 200 years later, computers were now there to help check lots of numbers. They managed to do a direct search on this computer and find a counterexample, so a situation where this is not true. So there's no point in seeking, you know, any further proofs because it's definitely not true. Now, back to our question, which was is it true that the sum of four consecutive integers is always divisible by 4? I know that I've shown that it's not. I'm actually going to show that it's never true. So I could, in the same way as part 1, have x minus 1 plus x plus 1, but now add an extra term, plus x plus 2. And this, remember, becomes 3x, so I get 4x plus 2 overall, which leaves a remainder of 2 when dividing by 4. So the sum of four consecutive integers is in fact never divisible by 4. And that wasn't needed, but I think it's just a nice little addition to this question. Finally, part 3, for which k is it true that the sum of k consecutive integers is always divisible by k? Now we know it's true for 3, we know it's not true for 4. It kind of makes us think, or makes me think at least, that it's going to be true potentially for odd numbers, because I'm going to, for 5 numbers, for example, I could have x minus 2, x minus 1, x plus 1, and x plus 2. I can see that it's cancelling down. And the same is going to apply to 7 and 9 and so on. So we're talking about, of course, k being greater than 0. That's implied, but I'm just going to write it there anyway. So first of all, k, okay, this is going to be case 1. K is odd. Now, if we've got k numbers, then there's actually going to be, let's say I've got 1, 2, 3, 4, 5. There's going to be a middle number and then 2 either side. And what I have to do is do 5 minus 1 to tell me how many are going to be the other side of the middle number. And if I divide by 2, which gives 2 in this case, it tells me how many are to the left and how many are to the right of the middle number. So there's going to be, overall, I've got 5 here, but it's going to work similar for k. It's going to be k minus 1 over 2 numbers either side of the middle. Number, and this will help me write my sum out. So I'm going to have, instead of having x minus 1 or x minus 2 in the case of the 5, like I just said, I'm actually going to have x minus k minus 1 over 2 plus x minus k minus 1 over 2 plus 1. I'm not going to be minusing quite as much. And then I'm going to continue to add these. I'm going to add my middle number. And then I'm going to add a load more. It's going to be x minus 1, x plus 1. And then I'm going to get to x plus k minus 1 over 2 minus 1 for the second last, plus x plus k minus 1 over 2. And these are going to cancel just like they did before. This is going to cancel with this. So overall, I'm going to end up with kx. See, that is really why we want to use this middle number like I did right at the start of my proof. It just makes life so much easier in these situations. I said like we could do it for this one, but the proof, it would be so much harder to use this idea of proof if I was saying the smallest number was x. Whereas now I can, I think it would be possible, but it's so much easier here. So I can see that I get kx, which is always, it's going to be divisible by x, sorry, by k. So I've proven that it's true for all odd integers k, or positive integers, we should say. Let's take a look at case 2 when k is even. So remember, this didn't work for when k is equal to 4. So I'm going to attempt to show that it's never true. And if k is even, then k minus 1 will be odd. So what we'll get here is actually k minus 2 over 2 numbers either side of the middle number of the first k minus 1 numbers. This one is a bit more technical. And the sum of the first k minus 1 numbers will, just as for case 1, equal k minus 1x, just like we had kx before for when we had k as odd. And then we need to add k minus 2 over, x plus k minus 2 over 2 plus 1. Because just like we had before, this is our last number. This time it would be x plus k minus 2 over 2. So if I've got the 1 after that, it will be x plus k minus 2 over 2 plus 1. Hopefully you're still with me on this. So overall sum will equal k minus 1x plus x plus k minus 2 over 2 plus 1. This here becomes kx, and then I can write 1 as 2 over 2, which is then going to cancel with the minus 2, leaving me k over 2. And this means we will always get a remainder of 2 when dividing the sum of k consecutive numbers by k, where k is even. It happened with 4. We had 10 divided by 4 is equal to 2 remainder 2, but actually I've shown that it will always be the case. I'm just going to very quickly talk about this again. So yeah, my argument was, instead of looking at, just like I did with k, well, for k equals 4, what did I do? Here I wrote them out, and then I wrote x plus 2. It's the same idea here, but now, see, I wrote k minus 1x instead of 3x, and then I added on k minus 2 over 2 plus 1, which is actually going to be equivalent to this x plus 2. Just back down here. So I said that I've got k minus 1 numbers, it's going to be k minus 2 over 2 either side. I'm going to make the same argument to show that I get k minus 1 times x for the sum of those numbers. And then the one after that, the one that I've not considered so far, is this x plus k minus 2 over 2 plus 1. I've added that on, and I've shown that the sum becomes kx plus k over 2. Therefore, the remainder is always 2. Ooh, okay. I hope you're happy with that. It's a little bit complicated, but that is actually a full-on proof that it's never, we're never going to be able to divide by k when k is even. I'm going to finish by just showing you how the official solutions did this last part. So they said, okay, again, let's do a little investigation and show that it seems to be that it works when k is odd, but not when k is even. You could try 5, 6, and 7, and then try to show that it is true always when k is odd. So they went with k equaling 2n plus 1. I didn't worry about that, but my approach is still fine. And then they did a summation along the same sort of lines, cancelled everything down, and obtained the same result that I did, km. Therefore, we can deduce that it's possible. So it's, you might want to read and just see it's a slightly alternative route to proving it, like by writing it actually as an odd number. So now on to when k is even. what they then did is look at a counterexample. So in fact, add the first all the so say that k is equal to 2n and add all the numbers up from 1 to 2n. In fact, that's not the general case, is it? Because we could be talking about any consecutive numbers, but as long as we can show that it's not true for a count, like for an example for every single value of n, then that's enough to say that it's not always true. See, my result actually went further, and I showed that there will always be a remainder of 2, regardless of your summation. So I think it's more powerful, but as the question says at the end, we only have to, it's not necessary to actually show that it's never true. We just have to show that it's not always true. So I actually think this gets even more difficult than my approach, I've got to be honest, because they sum from 1 to 2n, which is actually known as an arithmetic series. In fact, the whole thing is about arithmetic series, really. Arithmetic series is just when you are adding things together and their difference changes by the same amount every time. So say 2 plus 5 plus 8 would be an arithmetic series because it's going up by 3 every time. With our case, it's just going up by 1. This is this is actually the sum of the first n, as far as 2n numbers though, so it's a very particular sort of arithmetic series, and yeah, but you might want to look into this. But to show for the first 2n integers, that their summation, there's a little trick. And there's a famous story about this actually. The mathematician Carl Friedrich Gauss, in fact, supposedly obtained this as a schoolboy to add up the numbers from 1 to 100 and obtained 5050 very quickly by noticing that we can take the summation 1 to 2n, or in his case it was just 1 to n, and write it in the opposite way round. So we can now spot that all the pairs add up to 2n plus 1, and we have 2n of them. So if I add two lots of the summation, then I get 2n times 2n plus 1. And hence we can divide by 2 to give a formula for the summation in this case, when we're just going from 1 to 2n, and spot that this is actually an odd multiple of n, because 2n plus 1 is going to be odd, because we know that 2n is even, and also what we can see, yeah, it's going to be an odd number, and there's no way that this can be a multiple of 2n. So we found a single counterexample for every single value of k, or 2n, and that is enough to show that it's not always true. So I think this is, yeah, pretty tough to realize to do this, but it maybe gives you some further insight into the problem. It also gives you some little things to investigate if you're interested in, because typically you look at arithmetic series sometimes a little bit GCSE and then in much more detail at A level. But hey, it's never too early to start, so have a little read about Carl Friedrich Gauss. I mentioned Euler earlier on in the question as well. There are some accessible things to read about them. Well done on this pretty challenging question.